Thumbs
Yeah.
in.
Yep.
You started?
You're live.
Oh.
Yeah.
All right, I'm told that we are live. Let's wait. Let's wait like half a minute. All right. Hello, everyone. Welcome to another episode of Quirkcast. This is your host, Tim.
And I'm Mikey.
And this is Sahil. Welcome everybody to a brand new exciting episode. It's episode 2 of season 2. And if you're just tuning in, yes, we have multiple seasons. So we're in season 2 now. So before we get started, if you haven't joined our Discord channel, please do join it and ask questions there, and we can get to them. And if you're on YouTube, do post any questions that you might have during the episode so we can tune in and answer your questions. So without further ado, so I guess Tim or Mikey, I was thinking, I like see all these articles about astrophysicists say, oh, Einstein is wrong, or is Einstein wrong, and like kind of just trying to, just stomp Einstein out. And my question is like, why can I get in on some of that and like crush Einstein myself? Like, how do I do that? Like, tell me, what's the magic formula?
I feel like I would just, before I guess we get into that hornet's nest, it's probably not the astrophysicists themselves who are saying it, because like, reputable astrophysicists at upstanding institutions would not make claims like that. It's probably like the science journalists being clickbaity, right? And I don't know, I feel like I could be pretty confident of that, because I don't think any scientist really thinks in that way. But it's kind of annoying that this is like the predominant kind of title you see on headlines. And I think it gives people a really distorted view of how to think about science.
Yeah, I think within the academic realm, it's like a career death sentence if you use the words like paradigm shift in like a talk or something. These are things you don't talk about. Like, other people can call your work paradigm shifts or like proving something wrong, but you yourself don't say that. Scientists are often very cautious. So I do highly doubt that physicists themselves would say, hey, Einstein was wrong, I prove him wrong, and so on and so forth. But of course, that's not to say that Einstein as a scientist was probably wrong a lot of the times. Let's just get that straight out the door. I think every scientist probably would be wrong like on average multiple times per day, probably more wrong than not wrong, right? I think.
Yeah, it's a numbers game for sure.
Yeah, like in order for you to have a good career, you always have to think about crazy ideas, and most of them are bad. Like, but then that's the name of the game. You rule those out in your head right away, and then you put forth good ideas that have a decent chance of being right. So I think the literal question, was Einstein wrong? Yeah, probably he was wrong quite often. but I think a lot of those clickbaity articles, and here's one I found, right? It says, was Einstein wrong? Why some astrophysicists are questioning the theory of space-time? But it's a bit sensationalist, isn't it? Right? They're actually not attacking Einstein directly, but they're attacking Einstein's theory of space-time, this theory of relativity. I think that's what we're getting at.
So what you're saying is all I need to do is be an infallible human being, and I will have defeated Einstein, basically.
Probably, but that's impossible. So sorry, you can't. You can't win just yet.
Yeah. So I guess this question of kind of, so if we jump to the theory of relativity, asking, is it wrong? Like, how do you sort of think about that question? Yeah, that's
a very tricky question. Maybe I can take a step first. So when we say a theory is wrong, I think we mean very different things than what a lot of people think when a theory is wrong. I think in the general public, when people say, oh, right or wrong, it's so binary. It's like it's either right, 1 + 1 = 2, or 1 + 1 does not equal 2. And I think we're taught in school that theory so in the scientific realm is falsifiable. So it's right, and all of a sudden, when something falsified, it is immediately wrong. But practically, that does not work. The way we think of physics is almost like layers of onions. Different laws of physics are valid in different regimes. So, for example, Einstein's law applied to, for the most part, applied to astrophysical large objects, planets, the universe, and whatnot. And you can argue that Einstein proved Newton wrong, kind of, because Newton has his own theory of how planets move. But yet we still use it. I'm pretty sure NASA used probably Newtonian physics to calculate some of the rocket's trajectory, right? So even though, in a sense, Einstein proved Newton wrong, was Newton really wrong though? I mean, it's the theory is still being used. It's still valid in some regime, right? So I think it's not. So I think so what's the takeaway? I think in the public's eyes, right or wrong is so binary. It's either right or wrong. It's totally right or totally wrong. But in science, it's not that. Some theories are always right in some regime and wrong in other regimes. And the same is true for relativity as well.
So I think there's a parallel to something I heard regarding flat earthers. So I think it goes something like the only true flat earthers are photons, because as they're looking at the earth, everything's just collapsed into like a pancake. And so in the context of like a photon's reference frame, flat earthers are correct. But outside of the photon's reference frame, flat earthers are incorrect. Is that kind of how to think about right and wrong in a certain sense? Or like
flat earthers don't know. No, I don't know how to think about that, because
well, I don't want to give credit to flat earthers. I mean, on some level, you can think of the earth as flat. I think on some level, that's totally legitimate. Like in terms of the human scale, like you drive a few hours away, yeah, the earth looks damn flat. That's fine. You can say that. But that tells you nothing what the earth looks like when you zoom out. In some regime, the earth is flat. That's fine. You just can't claim that it's flat in all scale. So,
but that's also giving flat earthers a lot of credit, though. I mean, flat earthers believe a model for the universe in which the earth, something like a disk or something. It's a very specific model for what the universe looks like that is, a fantasy.
Yeah.
So.
Well, I think that's the error that a lot of people have when they take a lot of theories. So, I mean, definitely don't want to give flat earthers credit, but you should not say things 100% one way or another. Like, just because you observe something does not necessarily mean that it generalizes 100%. So that's the error, for flat earth observation. Just because you see that the earth is flat here does not mean that you zoom out all the way. It still will be flat. But I mean, I hate to use that as an analogy to Einstein's theory, which has been extraordinarily well tested, right?
No, I think there's a way to tie it in. I mean, if you think about it that way, like, just to summarize, I think what the main point of what Tim was saying is that people think that theories replace each other, but through 300 or 400 years of developing theories, it turns out that more successful theories don't replace the previous one, but they subsume them, or they generalize them, so to speak. So once you start seeing that pattern, or the observation of that pattern, I would say, has been the driving force of kind of like all of physics over the last maybe 100 years, when I think people really started noticing these patterns of unification, that the goal is to find the theory that subsumes the theory before it, not replace it. And I think that's the misconception that people have a lot when they think about being right or wrong, or theories being right or wrong. So flat earthers, I guess, would be on the most primitive form of that spectrum, where like their explanation for the world is only consistent with what's immediately in front of them, and without any other considerations of generalizing to other scenarios. That's not even like part of the spectrum of thought, I think.
So are you saying that like when you say subsumes, it just means that in certain limits, one theory reduces to another theory, kind of this like reductionist point of view, or not reductionist, but like the other way, coarse graining, like more coarse graining. Sorry, yeah, that's what I meant.
Yeah, yeah, you can, I'm sure there's like a pretty diagram you can draw of all the different kinds of theories that people usually talk about being right or wrong. Quantum mechanics at short distances, when you zoom out, it reduces to classical mechanics and makes all the same predictions that classical mechanics does. And when you get close to massive objects, we use general relativity, but as soon as you move away from them, gravity reduces to the Newtonian picture. So in the Venn diagram, Newtonian physics is one proper subset of general relativity, in the same way that classical mechanics is one proper subset of quantum mechanics.
Gotcha. That makes sense. Um, huh. Has it ever, this is kind of a little bit of an off tangent sort of question, but like, has there been anything historically that you've seen that like there used to be this kind of all this work built up upon this school of thought, and just was complete bogus, and it's sort of another school of thought got developed and added on, and like that expanded out, kind of this like evolution of ideas?
I think that's a really good question, because like kind of like, you know, we talked about theories subsuming each other. That's kind of like if you're looking at the main branch of the evolution, right? And so, you know, we kind of like railed against the idea of like theories being wrong because of the fact that they subsume each other. But there is that sense in which a theory can actually really be wrong, where it's an idea that hasn't, where there isn't enough time to test it that well. But a lot of people are thinking about it, so it kind of develops into its own thing and is later found to be invalid. I think the most famous example would be like loop quantum gravity, maybe, or things of that nature. But if you look
maybe
at these
like,
programs, they rarely last
like,
past like 10 years, right?
Maybe like the ether, maybe the theory of ether, I guess.
How long did that last? Maybe another, also like 15 years, right?
Yeah, something like that. But
Yeah.
there were many like showstopper observations that were inconsistent with ether's theory, that, you know, like the branch was not doing very well to begin with. It was kind of like a Wilteri branch. So
yeah. But that's the process of science, right? Is to hack off these unwanted branches from the main tree.
Yeah, so coming back to a lot of those articles, I mean, some of those articles are based off of like legitimate scientific publications. And obviously, when you go to those scientific publications, they're not making claims that are anywhere close to how wild the clickbaity titles were, right? They never mention anything like, oh, Einstein was wrong. Usually what happens is just that if you imagine the trajectory of Einstein's theory as sort of like this analogy of a branch coming off, you're really just looking at like one tiny sub branch in this big branch, and it just slightly different from how we expected it. Basically, that's how it is, right? Like some very particular predictions of maybe Einstein's theory are slightly not exactly as what we would see when we make observations. Like maybe the galaxy distributions are slightly different, blah, 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 yada, 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 right? But those are like tiny little, what is it, perturbations almost. Because we don't expect, like, come on, like when you say Einstein's theory of relativity, once again, it's not just like it's one theory, right? Einstein's theory of relativity is almost like a language, like we mentioned before, like quantum field theory. It's a language based on differential geometry. And there are many ways you can tweak the theories. You can add interaction to the theory, and Einstein's theory of relativity will still be valid. And that will lead you to slightly different predictions. And to some extent, that's the hallmark of a good paradigm, basically. Like it's flexible to some extent. So when you say, you know, Einstein is wrong, like Einstein never said exactly that his theory is exactly correct with these numbers exactly as given. He never said that, right? So to some extent, yeah, no, you just tweak the theory a little bit. I'm sure it will fit your observations more likely than not.
Huh. So then I guess like, how do you like intuitively it's easy, but like, how would you rigorously define in an intuitive way how a theory is wrong? Like if I predict certain properties that you just don't observe? Like, how do I think about that in terms of that's wrong in a certain sense? Like in particle physics, if there's a certain energy scale that I predict particles, but I don't see particles in that energy scale, like, does that mean my theory is wrong? Or like, let's say I go like several orders of magnitude higher and I still don't see it. Does it mean it's wrong? Or like, at what point do you consider it quote unquote wrong?
I view it really like as a seesaw scale. Like you look at all the things that the theory predicted that was right, including the ideas that it enabled, which produced ideas that were shown to be right, versus this inconsistent measurement that you see, and you ask which one begs the shift. Is it more likely that this one thing wasn't measured precisely and the theory's right, or is it more likely that this one measurement was right and all this other stuff is wrong, and we have to like completely tear down all the fabric and start from scratch? And I think that's the fantasy that people have in their heads when they read this kind of thing. Like, oh, is this result going to like, tear down all this existing fabric and change what we know about the universe? Yeah, and that's most of the theories they're talking about, particularly Einstein's theory of general relativity, which is the topic of this discussion, have produced so many experimental results that were verified, validated questions that we didn't even know we had, gave rise to new ideas that have been validated in other domains. So yeah, if someone wants to prove Einstein wrong, they have like, or Einstein's theory of general relativity wrong, they have a lot of work to do in compiling like a set of evidence larger than this body of 70 years we've collected.
Yeah. I mean, let's be more explicit here, right? Like Einstein's theory was right from GPS coordinates, which requires general relativity, to the orbits of like Venus when it gets close to the sun, to even like black hole mergers with gravitational waves, and the large scale structure of the universe, distributions of galaxies. I mean, there are just a bazillion different observational evidence from the tiny to the large. I think there are probably tabletop experiment. Has that been true?
Yeah. Like these.
Yeah.
I think so. Yeah. Not only that, but it gave rise to string theory, right? Which eventually made predictions and helped people model like materials and condensed matter physics.
Well, let's not go there yet. But I would say, yeah, I would say in coming back to Sahil's your question. I mean, you kind of flip the script and be like, well, if Einstein theories can't really be wrong, how can we like ever falsify it, right, scientifically? And I think that's the great thing of modern physics. A lot of theories actually tell you about that themselves. Like the theory screams out and tells it to you where it's wrong. This happens when a theory is pushed to its limits. And it's well known that Einstein's theory of relativity does not incorporate quantum mechanics. It does not involve things like quantum fluctuation, for example. And because of that, it makes no prediction about quantum mechanical behavior of gravity. So the theory itself, the setup itself, is screaming to us where Einstein's theory is incomplete. So from that regard, Einstein's theory is wrong from the get-go. It just is wrong because it doesn't have quantum physics, right? So, but then now like if we ever are able to test the quantum mechanical behavior of gravity, Einstein's theories will be falsified right away.
I guess like, so falsified means that the predictions it makes are wildly diverged from what you actually observe.
Wait, so, because Einstein's theory doesn't even predict that. Like for example, imagine you can look at the fluctuations, let's say, of gravitational waves, which is probably impossible, right? In a quantum mechanical way, or like black hole evaporation, you can measure that, which is probably not possible right now because the Hawking radiation is really dim and also takes a huge amount of time. But imagine you can measure that, then you can argue that you have falsified Einstein's theory of relativity because Einstein's theory of relativity just doesn't include those facts, right? It just doesn't include Hawking radiation, right? But very few people would like scientists would really say that, hey, Einstein was wrong. It's just that Einstein's theory was not applicable in those cases. And sort of Einstein's theory, I guess, if it was sentient, already knew that, kind of. So it's no
Yeah,
surprise, basically.
yeah. These articles would be more accurate if they said, was Einstein's theory not the end all be all of science and explaining everything there is to explain ever for all time? And that's a much less interesting answer, I guess, so it doesn't sell as much.
Huh. So I guess like I guess it might be helpful to the audience if there could be like a kind of like a tree structure that we could describe of how all these different theories are connected to each other, if possible. Like how would you guys, like from a reductionist or coarse graining point of view, kind of relate different theories to each other?
Okay, so classical mechanics being a subset of quantum mechanics.
It's not necessarily like a straightforward tree. There are branches and there overlaps, there are non-overlap.
Okay, start with no, you start with string theory is the most general one, and quantum field theory is some subset of that. Quantum mechanics is some subspace of that.
Well, string theory has two branches. I think in some limits, string theory can straight up give you general relativity, and in other limit, it can straight up go to quantum field theory. And quantum theory and general relativity has a small overlap, right? They don't play too well with each other, and those branch down. So quantum field theory, there's a branch, quantum physics, and then there's quantum physics comes classical physics. And general relativity can also go to classical physics, and then classical physics overlap. Is that fair picture?
I don't know. I couldn't start to get all that. I think the simple way to think about it is there's two axes, right? There's the size axis, and then there's the energy, the massiveness axis. String theory is like, describing the whole thing. Small, and then I talked myself into something I can't talk my way out of.
It's complicated. There's also cosmology too. Wow, I don't know where that fits in.
Isn't cosmology like in a specific case of general relativity kind of a sense?
It's more or less, yeah. But there's some extras because there's this perturbation, like quantum. It's general relativity with quantum fluctuation. So it's like general relativity plus.
Cosmology is more like a story that is written in the language of these different things, right?
That's fair. I guess like where does like I guess like how should one think about general relativity in like classical I guess like actually wait, cosmology is like where you kind of zoom out on such a large scale, right? Like generally, I mean, unless you're talking about quantum cosmology.
I don't think you can.
So
I hold on. I think now we're really getting into a discussion about like the taxonomy of theories. Some people, when you're young, you hear like people who want to sound smart going off about the definition of a theory versus a hypothesis versus a this and that, and they have all these like random delineations for what separates these things. But in practice, everybody uses the word theory just loosely to talk about anything. But I think it's important to make the distinction here because kind of what we're talking about in a previous episode, like a lot of times when we say theory, like quantum mechanics or string theory or something, we're really talking about a language that can describe many theories. And cosmology is even a more specific instantiation because it's not even like an instance of a theory, but it's actually a story that we can never actually verify because we can't make another universe in a controlled setting. It's kind of like a story that it's like an archaeological history almost that involves physics-based explanations and extrapolations.
Yeah, and also a lot of times because physics is a very practical discipline, and you kind of take a little bit from everywhere. Like we know the like in terms of practical physics paper writing, right, or studying something, because every theory is basically incomplete. There are no theories that are completely self-consistent. So when you do a calculation, you say, hey, first of all, how do I approximate this calculation? And whatever you need, it could be general relativity, It could be a little bit of particle physics. It could be a little bit of thermodynamics, and it could be a little bit of, I don't know, whatever it is, whatever physics it is, or you can mix in a little bit of string theory if it's needed, to cook up whatever calculation you want to do, and then you get the results and you interpret it. So it's kind of like a mixed bag of everything. so it's never like a clear separation that be like, hey, like I'm literally just using Einstein's theory to do this thing. I think that's fair, right? It's never clear, the separation. There's always some overlap, and that's where
that makes it
physics
even
comes
more
in.
like archaeology, right? Like the way archaeologists have different tools, like like digging tools, dusting tools, that they use for different purposes. Each plays a specific role in piecing together this picture. It's very similar to the way I think we approach cosmology. It's almost a game of like, for a while, it's like, what tools can I use to solve a problem that no one's thought of yet?
Huh. What about, would you even give the kind of archaeological example for like even more I guess down to earth physics experiments like material science or even particle physics, kind of needing to observe the past in order to make inferences about the laws of physics?
I think it boils down to the repeatability of controlled experiments. Our inability to perform a controlled experiments about the early universe, I think, makes it categorically different from what we usually call theories. Whereas I think in material science, typically you can reproduce results in a lab or in a small controlled setting where the environment is very carefully manipulated.
Huh. So what about, so then how do you guys think about like the notion of repeatability of experiments? Like what, I guess, just like, yeah, it may be a very obvious question, but I'm just curious to hear your take on it. Like,
no, it's not obvious, especially for theories that are almost as grand as like general relativity. I mean, obviously for material science, it's easy. You can just, have another piece of the same material and do some tests on it. But for relativity, it depends on what you're doing. For example, if you're studying properties of galaxies, yeah, you can just look at different galaxies and then get gather statistics. But of course, if you're studying grand properties of universe, I mean, we only have one universe, so I mean, you can look at different patches of a universe, but there's a limit. To some extent, if you study the largest structure of a universe, there's only like a handful of independent patches. So this sort of repeatability is a bit of a conundrum, and in fact, I think there is controversy, right? In terms of the large scale structure of the universe, we see like a slight, like a cold spot in a particular patch of our universe, and for a while, I think it's not clear whether that's a hint of something new that was unexpected, or that's a fluctuation just because we don't have another universe to check out. But it's difficult. So it's not a silly question.
Yeah, it's funny. I never thought about it that way, but it's almost like you need multiple copies of your experiment in order to be repeatable. And the bigger your questions get, the less universe there is to split into copies.
And it's not just space and time. We can't wait another 10 billion years to have another Big Bang.
Yeah.
So there was a comment that one of the audience members made. It was asking for thoughts. It says everything that comes from the human mind is incomplete. There'll always be gaps, inconsistencies, failures, etc. Thoughts? ?
Oh, I did.
I guess I can take that or add to that question that I think goes with what Mikey is saying, that this is essentially a story that we've constructed that has some sense of continuity to it, and I don't think it's a guarantee that story will continue, but it's holding up for now.
Yeah, I mean that's an interesting thought, and I think we might have lost Mikey due to internet connection.
Oh,
yeah. But anyway, we we can continue the discussion between you and I. Yeah, so that's an interesting thought. So it's quite plausible that there's some human limitation on what we can understand, and it's yeah, and probably that plays a certain role in the theories we built. And I think we had another episode way back on the incompleteness of physics. And part of that incompleteness could be due to the way language is structured, the way we prove something. Because every time you prove an experiment, the experiment has to be explainable in words. And that tells you that the way to prove something has to be countable, because you can always count how many ways you can, structure words together to make a statement. So it's quite plausible that maybe the way to understand the world, maybe it's not through these discrete words. Maybe it's through some, I don't know, something more quantum mechanical, and we clearly are not very quantum mechanical objects. But this is very speculative. So I imagine, yeah, that there definitely are some limits to the way we think. But unfortunately, this kind of it's a bit of a circular logic, because we wouldn't be able to know because we are stuck by these constraints. So how can we tell? But I mean, we should just keep trying to some extent. There's no reason to despair and be like, wow, too bad.
Yeah. So we're running up against time. I don't know if Mikey will be coming back, so we'll just keep going, and and then if he shows up before, then good. So I guess like what I'm getting from this is, in order to crush Einstein, I basically have to either Einstein's theory of general relativity, I need to produce enough evidence to falsify the 70 plus years of body of work that have been used to substantiate it, or I just have to be infallible, and then I'm good.
Well, I think it's a little even a little harder than that to truly falsify Einstein. You have to say that, well, Einstein's theory anyway. You have to say that every possible combinations of Einstein's theory is incompatible with whatever experiment. Like that, like first of all, okay. And even when you do that, you don't want to sound kind of, I don't know what's the word. You don't want to sound kind of pedantic, because we know Einstein's theory is already wrong because it does not include quantum mechanics, right? So to really, I think to really legitimately satisfy some of these clickbaity articles titles requirement, it would have to be some sort of insane surprise. It has to be like, holy crap, like Einstein's predict planets move this way, and all of a sudden it actually doesn't move this way in such a weird way that like no versions of Einstein's theory will be able to accommodate that. That is highly unlikely. I mean, given 70 years of evidence. So I would almost say it, in a hesitant way, like as this stands, Einstein probably just isn't wrong. Like however you slice it, Einstein's theory just isn't wrong. It's correct in its regime of validity. And we know pretty well what its regime of validity is. And when we finally prove it wrong, it will be no surprise. It'll be like, yeah, we kind of know, it's Einstein's theory probably doesn't apply.
So what I'm hearing is infallibility it is, and then we're done. All right. So I have my answer to my question. And I think on that note, I'd like to thank everybody for joining us, and we'll see you all next week.
Yeah, see you all next week. Thank you for joining us.
Yep. Bye.
Bye.